Hello. Today we're going to move on with Chapter 18. And Chapter 18 is all about the ray model of light. So the ray model of light just assumes that light travels in straight lines. And here we see a laser show and all of these laser lights passing through the air. Honestly, a laser is a pretty good approximation of a light ray. It's a pretty good approximation of a light ray. And we'll talk about why that is, what that means here in just a second. In the meantime, we can have our own little laser show. Whoa! Okay. In this chapter, our goal is to understand reflection, which is when light bounces off of something, off of a surface. We're going to understand refraction, which is when light bends. It bends when it moves from one medium into another medium. And we're going to use those tools to see how we might be able to form an image through reflection, as shown here in this mirror, or through refraction, as shown here with this magnifying glass. So to kind of recap a little bit, we're talking about the ray model today. And that's appropriate when trying to understand how light interacts with objects that are much larger than the wavelength of light. And to refresh, we had the wave model, which we talked about in the last chapter, which is appropriate when trying to understand how light interacts with objects that are comparable in size with the wavelength of light. And of course, we also had the photon model, where we treat light as a particle. To kind of refresh, in the 1800s, there were a series of experiments which demonstrated conclusively that light is definitely a wave. And so that last chapter was really 1800s physics, maybe early 1900s physics. The particle model, of course, there was a series of experiments in the 20th century, which proved conclusively that light is also a particle. And so that was the photon model, which we learned about a couple chapters ago, and that's 20th century physics. Now we're talking about the ray model of light. And in the ray model of light, we say, well, you know what, we don't really care what the fundamental nature is. Is it a wave? Is it a particle? We kind of don't care. We know that light behaves in certain ways. How can we describe that, and what can we learn about it? And so now we're really jumping back to Newton. And so we're kind of going back in time here. This is 1700s, 1800s physics. So, what is the ray model of light? Well, we say that light rays travel in straight lines. Light rays can cross. An object is a source of light rays. And so any light rays come from some object, right? So where are the light rays? Here, of course, my laser pointer is a pretty good source of light rays. In my blackboard here, I've got some Christmas lights in here, and each one of those is a source of light rays. Light rays travel forever unless it interacts with matter. So it might bounce off of a surface, it might scatter off of some particulates in the air, it might bend because it went from one material into another, or it might actually get absorbed by some material. And we can understand images formed, including the one that is formed on our retina by our eyeball, by thinking about bundles of rays which diverge from an object. So again, light rays will travel forever unless they interact with something. Here I have my green laser pointer, which is nice and bright. And if I shine it here, you can see this nice spot on my blackboard there. But of course you can't see the ray traveling through air. Why? Because there's nothing for it to reflect off of. Now, I may be able to make it show up if I put some chalk particles in the air. Can you see that? Yeah, a little bit. This is why the laser shows have a smoke machine. There you go. You can see it bouncing off of some various dog hair, chalk particles, all the various things that one finds in my basement. Anyhow, what I was trying to demonstrate there was scattering of light rays. So those light rays will travel forever unless they bounce off of something or interact with matter in some way. So sources of rays, like I said, a laser pointer is a pretty good model of a light ray source. We can also have a point source, and basically a point source is something that emits light in all directions, but only from one single point. And a Christmas light is a pretty good model of a point source. An extended source illuminates from various parts of the object. So we can think of an extended source like a light bulb as being a number of different point sources, a whole bunch of point sources sort of smeared out. And so we're getting light from this part of the light bulb, this part of the light bulb, and this part of the light bulb. A parallel light source, a flashlight is a pretty good approximation of a parallel light source. Your headlights on your car produce a beam of light rays that are pretty much parallel. And a object that is very, very far away also produces approximately parallel light rays. So if we were to look at the sun, not with our naked eye, of course, because that would not be safe. But if we were to look at the sun or at a distant star, we'd say, well, that's a pretty good approximation of a bundle of parallel light beams. There's kind of a lot on this slide, but if you're viewing a point source, then anyone can see it. Because again, a point source emits light uniformly in all directions. So no matter where my eyeball is around that point source, then you can see it. Same with an extended source. You can see this from any angle if it's emitting in all directions. However, seeing a ray source, as I was trying to demonstrate a moment ago, these rays only scatter off of some sort of particle in the air. And so if we were to jump back to this picture, the reason we can see these beams going through the air is because there's probably a smoke machine going. And so they're filling the air with small particulates, and that's what the laser light is bouncing off of. If there was truly a dust-free room, the laser show would be very boring. A lot of objects are, we do see it by reflection. They're not actually self-luminous. Like these three objects here, the laser pointer, the point source, and the extended source, those are self-luminous. But you can see this blackboard, not because it is illuminated itself. Right? This little mark that I'm making on here, right? That chalk is not it's not self-luminous. You can see that because light is bouncing off of it and into, in this case, the camera on my computer. If we want to think about how shadows are formed, from a point source, we get a nice crisp shadow. And so the sun in the sky, it produces pretty nice crisp shadows. It's a long ways away. It's not quite a point source, but it's a small source relatively. It produces nice crisp shadows. However, if we have an extended source that is large compared with the size of the object, we see a fuzzy shadow. And I think this picture really helps to understand that. This picture is taken, this is the view of bulb as seen from 3 points on the screen. So imagine that you were at this screen looking, and your eyeball is at point A. Well, notice if your eyeball is at point A, you still see part of the light bulb, most of the light bulb. And so you are definitely not in the shadow here. But if your eyeball was at point B, you would sort of see half of the light bulb. And so you'd have sort of a fuzzy shadow there. Whereas if your eyeball was at point C, we would notice that the entire light bulb was covered and be completely in the shadow. Which is why we get the fuzzy edge to the shadow, because it's possible for a point like B to be in the shadow from part of the light bulb, but not from all of the light bulb. So the law of reflection is fairly straightforward. It simply says that the angle that the light ray comes in at is equal to the angle that the light ray leaves at. And notice that I'm always going to measure angles with respect to the normal. Now, you're not going to get yourself in too much trouble here with reflection. But once we start talking about refraction, which is our next topic, you are going to find that it's really important to use this angle and not this angle. That's a really easy mistake to make, to accidentally use this angle. I'll point that out again as we go through these slides. So again, the law of reflection, fairly straightforward. It simply says that light bounces off at the same angle that it came in at. And so here we see how that can give rise to an image. So here I brought this mirror down. Let's see if I can't demonstrate something with this here. And when I look in this mirror, I see a picture of me. Not a picture, I should say an image of me. And when I look in this mirror, it kind of looks like there's an Ansel right about here. There's not. Thank goodness there's only one of me. And it's right here, right? Over here, that's not me, but my brain is fooled into thinking that there is something right over there. We call that an image. We call that an image, right? Oh, look, this is really, see, look, this is what it looks like to me. So, here I have this lovely, this is an antique vacuum tube, like one might put in I don't know, guitar amplifier, for example. You can see here, there's actually a lot of images happening here, because one image that's happening is the reflection in the mirror, right? So it looks like there is a box that is somewhere, I don't know, right around the location of my chest or something, right? There's only one box, right? That other one is what we call an image of the box. And we call that a virtual image because there is no light being emitted from, this point right over here where it kind of looks like that box is, right? It kind of looks like it's back here behind the mirror. But there's no light being emitted from there. Your brain is fooled into thinking that that is happening. There's another image happening in this situation, and that is the image that is being formed by the lens on my camera on a CCD, which is a computer chip designed to be sensitive to light. And so there's actually a lens in my computer that's focusing the light from this box onto a computer chip and converting it into an image, which presumably you're going to see at some point. So that's another interesting image that we'll talk about in just a second. So here we see on the PowerPoint slide, we see a schematic of how this works, right? We know the object is actually right here. The light rays bounce off of the mirror, but our brains have evolved to understand the ray model of light to a certain extent. Our brains have evolved to just assume that light rays travel in a straight line. So our brains interpret this as, I know where these rays are coming from. They're diverging from a point right over here. There must be a tree over here. Our brains are fooled, right? And so this image occurs because our brains are fooled into thinking that there's a tree over here. Our brains are fooled into thinking that the light is coming from here. Really, it's coming from right here and bouncing off of the mirror. So this is the basic idea of forming an image. Now we can distinguish between two types of images, a virtual image and a real image. And this will become a little bit clearer when we start talking about lenses. We'll get into it a little bit more depth. We call this a virtual image because, again, the light is not actually coming from this point. The light is actually coming from over here. Our brains are fooled into thinking it comes from over here. That is a virtual image. We'll find that there are such a thing as a real image, and again, we'll get to that when we talk about lenses, where our brain is fooled into thinking that the object is somewhere where it isn't. And in the case of a real image, the light is actually coming from there. And we'll see how that looks here in just a minute. So here is an example. An object is placed in front of a mirror. The observer is positioned as shown. Which of the points shown best indicates where the observer would perceive the image to be located? Why don't you pause the video and see if you can't figure this out. Okay, to figure this out, let's analyze the situation. We've got this tree here, and rays are diverging from it, and what they're doing is they're bouncing towards my eyeball. So, here are some rays. They're bouncing off of here. The angle that they come in at is equal to the angle that they leave the mirror at. Oops, this arrow's going in the wrong direction. Sorry, that arrow was going in the wrong direction. Okay. Okay. So there are rays. Now our brain thinks, I know what light rays do. They travel in straight lines. So my brain is pretty darn sure that there is a tree over there. I think C is the best choice. Again, our brain is fooled. And this is what we call a ray tracing. And I'm not really sure how you can figure this out without a quick picture like this. You may be able to visualize this picture in your brain, but this is the logic.